Okay, good morning. So let's continue with our linear stability analysis of the Kelvin-Helmholtz instability. So the interface instability problem. Okay, which we had these equations. So we have the Okay, so this is our system of differential equations. Remind us of the problem is S equals to 0, S equals to 2 pi. This is epsilon. We have like a shear flow at infinity plus, away, which is plus u minus u. Okay, this was from last time. Then we write the solutions. Okay, where I want to remind you where okay, so so that means for epsilon, right, stationary solution. So this is for epsilon equal to 0. This satisfies this, right? It's easy to check if we know Clemelli's formula, right? So check using the result of Clemelli's theorem of coming from above, coming from below, which tells us, right, the stationary solution is this one. Okay, so it gives us, right, this singular integral with here s minus s prime gives us this jump in velocity. And how do I know that? It's not easy, but it's easy if I know Clemelli's theorem, right, which one has to prove things coming from above, below, blah, blah. Now, we want to see that this problem, we're going to learn now that this problem is ill-posed when sigma, the surface tension, is equal to 0. It's linearly ill-posed when sigma is equal to 0. Looks complicated. It is complicated. And as I will write, what I did last class is that it becomes simple as soon as we identify the Hilbert transforms of the function and of its derivative. So I have to write this again so that the class, right, the lecture makes sense. So let me write it like this. Order epsilon equations. How? After substituting 2 into 1, right? And remembering that the fact that this is a stationary solution means that the order 1 term of this expansion satisfies this equation, and then we're going to look at the order epsilon equations, right? So the order epsilon equation that is collecting all terms of order epsilon, the order epsilon equations, and rewriting these equations, this one in particular, into its real and imaginary part, we get this. I want to write this I'm figuring out here a way to write this in a simplified form so that we can save some time. So where the prime comes from S prime. Okay, so all the primes has to do with S prime. So this is system 3. So we did this last class. Okay, and I'm going to be able to write it here. We recognize, right, the following. Hilbert transforms, which are okay, and let me call this maybe square cross 1, squared cross 2. And this is what we saw last class. And then I'm going to write now that actually this, or this is the periodic version of this, and this is the periodic version of this. Okay? Again, we're not going to show how to deduce this, but it's a result. So fact, some facts, not all, from Hilbert transforms, it has many aspects. I'll show you a few. The first one is that if I take the Fourier transform, it's minus I, so this is the Fourier symbol. Of this operator, or also called multiplier. Okay. And let me write here. Periodic versions of 1 and I'm going to write already with this result, which is going to be useful to us. Okay, so what do I mean here? This is playing the role of, I call it F. Okay, so this is the Hilbert transform, boom, 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 of F in the periodic case. Okay, and I'm already giving you another result. If F is a Fourier mode sine, it gives me back minus cosine. Okay, so let me repeat. Okay, because I'm giving you results without showing the intermediate steps. Okay, so here's the Hilbert transform. Calligraphic H acting on F gives me this. And I'll show you today that this is actually, if F is the trace on the boundary, say of an upper half plane harmonic function, if F is the trace on the boundary of a harmonic function, this is the trace of its harmonic conjugate. I'll show you this today. So here's one fact of Hilbert transform. Another useful fact of Hilbert transform for us today is that if you take this integral from minus p infinity to infinity, and you sort of sum up, you use all its periodicity, you can rewrite this from 0 to 2 pi, if the period is 2 pi. If not, you have to rescale. But if the function is 2 pi periodic, you can rewrite this integral over the whole line. You can rewrite this kernel of the type 1 over x. Right? There's a way you can do this with residues. There's a way to do it. And then this kernel becomes this guy, who sort of blows up periodically, right? To some extent. So it comes back as this guy. So this is the Hilbert transform of a periodic function, sometimes also called the Hilbert transform on the circle, just because of 0 to 2 pi. Okay? So this is the Hilbert transform of a periodic function. And because I'm going to do a Fourier analysis of that system, I'm already putting here a Fourier mode and giving you this formula that it takes the sine to minus cosine. Okay? And formula 2 in the periodic case becomes this. Also, I'm going to put either a cosine and a sine. I'll tell you why now I'm putting a cosine. I'll tell you in just 1 second. So because these are going to be the formulas useful for us. Oh, I see I have a typo in the notes. I forgot to put the square here. Right? Because we have the square over there, of course. So there's a typo in the notes. Never noticed this. And this is equal to K cosine KS. Never noticed this little typo. It doesn't really matter. People would easily recognize. Okay? The notes, it's missing this square here. Doesn't matter. So this is the Hilbert transform of the derivative. Okay? So this is the periodic analog of this guy, where I'm already putting, and I'll explain to you why, a cosine here, excuse me, and here I put the sine. Okay, I'll tell you why, just right now. So this formula here, these two formulas are going to be super useful, and they're going to make this complicated linear system of integral differential equations with singular integrals. Those formulas are going to make this reduced to a constant coefficient, very simple system of ODEs. How is that? Let me convince you of that, okay? So look, so let's go step by step so I also don't go too fast. Do you remember why I wrote my solution here as 2, right? Because I'm looking, my instability analysis is like a perturbation analysis in the neighborhood of the stationary solution. Okay, so for epsilon small. So that's why for the order epsilon equations, which are the first correction to this stationary solution, is the first good way to see things, but if you're close enough, okay? Now, look at this. I want to do a Fourier analysis of this system. Okay, so if this system is linear, so if I do a Fourier analysis and I use a Fourier mode, which is a e to the I ks in here, for example, just to do a Fourier analysis of the spatial part, right? Because it's linear, this is a cosine plus I sine, right? And I'm going to show you, note that the cosines, the real part, does not couple with the imaginary part, particularly because everything not only is written here as real part, but because a sine and the cosine do not couple. Look at this. If I say that the sigma has a cosine component and the y also has a cosine component, I differentiate the cosine twice, it's still a cosine. So I can cancel the cosine, and this will become an ODE in time. Okay? Now, here, think the same thing. So in this case here, okay, now I do it for the sine. If this is a sine, I differentiate it twice, it becomes a sine again. I cancel the sine of S, and this becomes an ODE for that mode. Here, if I put a cosine here and a cosine here, okay, look what happens. It comes back a cosine. Look here. Let me follow so the camera can follow me. If I put a cosine, it comes back a cosine. Which means then that I can cancel the cosine here with the cosine there, and it becomes just an OD for the temporal part. Think about separation of variables, right? A temporal part and a spatial part. Now here, the same thing. And here, look, there's this S here. So if I put a cosine for sigma, for gamma, sorry, this will become a sine, but the Hilbert transform of a sine gives me back a cosine. So that means all the cosines cancel, and all the sines cancel, therefore sines and cosines don't couple in this linear mode. If I had here, just so that you make sure you understand what I'm saying, if I had here not the curvature, but just the first derivative, I would put a cosine here, and here, sines and cosines would couple, right? Which means, in other words, mathematically speaking, is that even parts of the function do not couple with the odd parts of the function, right? Because sine is the odd part, and cosine is the even part of the function. So we're going to do just the free analysis for the cosine, because the exact same result, if you don't believe it, do it as an exercise. The exact same result we're going to get for the cosines is what we're going to get for the sines. Okay, exact same result. So, substitute, okay? So using the above result, so for example, let's see what my notation is. Yeah, let this guy be A1 of t cosine ks, x2 will be A2 cosine ks, and y3 be A3 of time. Sorry. That's my separation of variables. Cosine ks. Right? You can repeat the calculations we're going to do now with the sine. It's going to be basically the same thing, right? You just have to check what happens with the cosine here. Change just a little bit. Doesn't matter. But it doesn't really matter. So if we do this, right, then system 3 becomes this. See, it becomes an ODE for the amplitudes of these Fourier modes. So you can put the words you prefer, right? It's a separation of variables based on the fact that I know the results for the Hilbert transforms of the cosine, sines, derivatives, blah, 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 okay? And by checking that, actually, if I do for the cosines, the sines do not appear, and I can do it for the sines, it doesn't matter. It will be the same result. So now I get this very simple system of ODE, constant coefficients with all my physical parameters here. Well, remember that K is 2 pi, K is 2 pi over lambda. We know that, right? So for the typical perturbation that we're going to study, which is this one, K is equal to 1, right? Because this is from 0 to 2 pi. So lambda is 2 pi, so it's K is equal to 1. But we're going to learn, and I'm going to mention to you that, for example, I could have made a perturbation here like this, which is K much greater than 1, this one, right? A high frequency. But like, since, right, people at the time were studying this and wanted to see the effect, let's pretend also that we don't have the information. They have this, like, if I don't know what's going to happen, let me start, right? That's what Moore did. Let's start with the most simple mode, right? But you're going to see that putting all these modes gives us intuition of what Krasny saw in the numerics he did. Okay, so look at this now. If I have this system here, okay, where U is the strength of the shearing, K K is my wave number, that is my spatial frequency. Sigma is the surface tension, and rho is the density of the fluids. So these are physical parameters in the system that controls the amplitudes of the modes. Okay? Now, what would I do now? What would you do next? Now I gave you this system. This is very simple. So to finish off the stability analysis, linear stability analysis, because we're linearizing the problem, and therefore we got this linear system of equations, a complicated linear system of equations that was tremendously simplified by identifying, the periodic Hilbert transform. But now, to finish off the stability analysis, what do I need to find? What do I need to conclude from this system? Well, the problem is going to be unstable, right? Look, I start with an amplitude with its epsilon, small, right? This is the initial amplitude, epsilon, small. If this amplitude grows, there's an instability. That could be legitimate, physically legitimate to a problem. There are problems where the instability is legitimate. And here, people are trying to understand, well, is it legitimate that we're not sure? Maybe we have to put a new physical ingredient, which was surface tension, right? Before, with Krasny and Moore, there was no surface tension. So, look, if I look at the eigenvalues of this, I will know if the problem is stable or unstable. So, let's write here, look. Just think of this. If I diagonalize this matrix, right? If I diagonalize this matrix, so we will have these guys, right? If we can diagonalize it, then we can rewrite it in, as I showed you before, in the eigenvectors and so on, we can integrate, blah, blah, blah. And this is going to be then e to the I lambda t. Right? So the eigenvalues here are this. The spectrum for this matrix is this. Right, so this is a very important result. Right? The eigenvalues, right? Because then solutions are e to the I lambda t. Now look at this. Case, Moore, and Krasny studied was sigma equal to 0. Okay, no surface tension. Okay, but from our mathematical point of view, this is not a fluids course. If you don't know what surface tension is, no big deal. Okay, now look what happens. With no surface tension, lambda k is going to be plus or minus UK. Okay, so we're going to have solution has, say, two components in the sense of an e to the I lambda t and e to the I, or let me actually write it better, e to the I UKT and e to the minus UKT, because the eigenvalues are plus or minus this. Okay? But look, no, sorry, but there's no I. There is no I. Right? There's no I, because I made a mistake, right? Correct me if I do mistakes, silly mistakes or not silly mistakes, right? Because if I integrate this, right? If I had something like this, a mode like this, right? If I decoupled it, it would be just e to the lambda t, right? Why did I put the I in my, right? So stop me if I say something which is not right. So now I noticed it. So I have a growing mode and a decaying mode. So the important guy is this growing mode, right? Because this guy will make the solution grow indefinitely. And look what happens. What happens, what I can say from this guy, e to the UKT, if I look at here or here, actually here, it says two things. That the stronger is the relative current, the faster it grows. And also it says, and this was very important for Krasny to show the numerical results, is that it also says that the faster my perturbation is, that is, the more high frequency my perturbation is, the faster it grows. Because look, a fast perturbation is a smaller, right, wavelength, right? K is 2 pi over lambda. So this guy has a very short lambda, therefore a very high K. Because of a very high K, it grows faster. Okay? And I'm not going to show this here. I show it in the fluids course, but just as a comment, Krasny then understood that actually he had to do something about the round-off error of the numerical method, because the round-off error is high frequency, right? It's actually something, it's like noise, right, from calculation. And that guy would grow faster than the true interface perturbation, because the true interface perturbation is this guy. And the high frequencies came from noise. So people were seeing the computations go crazy and become garbage very quickly and could not understand. So some people would write papers mentioning about chaos and this and that. But Krasny was the one to point out correctly what was happening. It was basically the round-off error was growing so fast that it would contaminate the solution. The solution would look like garbage. So he developed a very simple trick, but very nice. It was called the Krasny filter, that he would filter the high frequencies, basically round-off error, so that he could see Moore's prediction that the curvature here would blow up in finite time and would blow up at the time predicted by Moore. Okay, so those were numerical tricks. This course is not numerical, but a few, I know some of you have numerical interest, so that's a comment. Okay, so this means, and put a graph here, that if I put K here, and I put here the growth rate of the instability, for the sigma equal to 0 problem, we have a straight line. See, you keep the U fixed, which gives us the slope, and as K increases, as the high frequency, as we go into high frequencies, okay, the growth rate grows linearly. And this problem is basically, this linear problem is ill-posed. So, right, so it's ill-posed in the sense of Hadamard, ill-posed in the sense, if we just think here, is that you have no control on the growth of your solution with respect to perturbations. Right, so there's not continuity in the parameters. And how can we see this here? Think let me start helping you, right? So you can think that all the perturbations, let me clean up, well, let me put this picture here. Look, I have my undisturbed interface, which is my solution, my stationary solution, okay? And we're going to play a game now that you can only perturb this guy with amplitude epsilon, very small, okay? So you can do all sorts of perturbations which are periodic. The first one, which is the one that looks physical, is this one, k equal to 1, right? So let's say here, let's think that this is the amplitude epsilon. Okay, so epsilon. So this is k equal to 1. And I can start increasing my frequency. Okay, and I continue increasing my frequency. I'm not going to do not more, or else I'm going to just color this in white. And I keep on increasing, right, my frequency. Right? It's like the Fourier series, because it's periodic. It goes, the k, this is lambda, k, which is 2 pi over lambda, oops, sorry, right? As this goes to 0, k goes to infinity, right? So I can see already, Lucas is already showing. So what happened? As k goes to infinity, the growth rate goes to what? Is unbounded, also goes to infinity. So the faster the perturbation is, the worse it is. So what people saw and drove people to wrong conclusions in the numerics is that they had a solution with, say, n points. They said, oh, maybe my solution is bad because I don't have enough points. So they went from n points to 2 n points. Then from 2 n points to 4 n points. And the solution just got worse. Instead of converging numerically, it just got worse. Why did it get worse? Because the growth rate became higher and higher. Okay, and it's unbounded. So we have here an unbounded growth rate for high frequencies. Frequencies in the sense of spatial frequencies, right? Frequencies in the sense of wave number k, right? Wave number k. So it's unbounded. Okay, so observing, knowing that, right? Noticing that, people then said, well, let's add surface tension, which is a physical regularization, which makes actually the equations more complicated, because now I have to control this guy, because sigma is here, and this guy will affect that equation, right? Krasny and Moore considered this guy constant, so they did not need this equation, right? There's this price of pain. But why people were interested in that? That was actually a problem I worked in my postdoc with Professor Greg Baker. Why were people interested in that? Because the linear problem became regularized. So note, as you know, since we're talking about PDEs and actually in the analysis course of PDEs, which is PDEs linear theory, one talks about well-posedness and proving that the problem is well-posed. And as it is nonlinear, things get more complicated. Here we were looking at the linear problem. So the linear, so here's the story. The mathematical problem that actually was first addressed in a numerical and in asymptotic, formal asymptotic way. The first question was, the linear problem, this was known for quite some time. The linear, and without using singular integrals, you can look at with the Euler's equations on, that the linear problem of the Kelvin-Helmholtz instability is ill-posed. I think you're okay with that, right? because of this. Keeps on going. High frequencies will grow with no upper bound, right? You keep on going in K. So that means if you make an epsilon perturbation, with a very high frequency, very quickly the solutions sort of diverge from the stationary one to the other one. Okay. So the linear problem is ill-posed. So the question that then was answered by Moore, I think he became very, very well known for that with his complicated sort of Fourier analysis, is that he showed, it was not a theorem, it was not fully rigorous, but it was very complicated and very ingenious, very intelligent. He showed that actually he answered the question that was the following. The question that people asked is, will nonlinearity restore the well-posedness of the problem? So you see what I'm saying? The ill, which is, the question would be like this. This problem here, 3, is ill-posed because perturbations grow without a bound, right? So you don't have that sort of continuity into parameters. In this case, for example, the amplitude of the perturbation. But then the people asked, is this problem here with sigma equal to 0, is this problem here because it's nonlinear, is this problem well posed? The linear one is not. If this one is well posed, that means that nonlinearity regularized the problem. Okay? In some sense. And people, then Moore showed that no. In what sense? You can start with a smooth, even C infinity, right? The sinusoidal perturbation here is C infinity. You start with a C infinity initial profile of the interface, and after a finite time, it does not have the second derivative because the curvature blows up. So that's what Moore showed analytically, and Krasny provided numerical evidence after recognizing that he had to control the round-off error that was growing, blah, blah, blah. Okay? So then people were then puzzled, saying, well, okay, so nonlinearity did not restore regularity, full regularity. So then people knew that surface tension regularized the linear problem. And the question that was at the time I was doing my postdoc, that we didn't answer, but we showed some things numerically, is that will surface tension still regularize the nonlinear problem? Because it regularized the linear problem. Right? Would that continue in the nonlinear case? So can you see, let me drink a little bit of water. Can you see why surface tension regularizes? That's an easy question, but then you have to know where to look, right? And you've seen this for the first time. So do you know why surface tension regularizes the problem, the linear problem? The answer, to help you, so to continue the question, the answer is in the eigenvalues. So here is the eigenvalues. Here is surface tension. And I claim that surface tension regularizes the linear problem. Look, there is a value of surface tension that depends on the density and depends on the shearing, which is U, that when surface tension And for, let me put it this way, and for a certain value of surface tension, there will be a K, a wave number, a critical wave number, where this guy will be bigger than this guy. When K is large enough, which depends on sigma, rho, and but the presence of sigma here is fundamental, there will be a critical wave number when this guy is bigger than this guy. This is negative. The square root of a negative number produces an imaginary number. So this curve here, for surface tension different from 0, the curve will be something like this. Okay? So this says that the growth rate is beyond this point here, the growth rate is 0, because the real part is 0 of the eigenvalue. And therefore, beyond this point, all Fourier modes would do what? Before this point, the Fourier modes grow. Right? But beyond this point, what do the Fourier modes do? They just oscillate. So you see, so this says, let me use this picture, this blackboard. This says that, for example, if I put this guy here and this guy here greater than the critical, this guy here grows in time, and this guy here just oscillates in time. So for numerical methods, the round of error would just oscillate the high frequencies. But anyway, from a differential equations instability problem, that's what we're studying here, we see that surface tension regularizes the linear problem. And the question was to see what it would do in the nonlinear problem. And at first it looked like there was still a singularity, but then with very high resolution numerical methods, people showed that it was not clear there was a singularity. It was looking like it was going to a singularity. Not so. It's a very delicate problem, very complicated problem, very interesting problem. And then, let me erase here. So you see, I was doing my postdoc working on this problem where people didn't know what surface tension was going to do. My postdoc was from 1989 to 92. Right? So basically 30 years ago, exactly. And then in 2003, so this is recent, David Ambrose, right, in the SciAm Journal of Applied Math, proved, right? Oh no, math analysis. Another journal proved that the well-posedness of the vortex sheet with surface tension. So see, in 2003, then there was a theorem proving, so you see how long it took, right? There was a theorem by David Ambrose proving that the problem is okay with surface tension. Okay, I have some time. Let me do one more thing with Hilbert transform, okay? Now, forget about this problem. Let me show you that actually Hilbert transform, going back to elliptic problems, it actually takes the trace of a harmonic function onto the trace of its harmonic conjugate. Okay? So, let me put more on Hilbert transform. So take this function here, this complex valued function, okay? So this is a complex valued function where the hypotheses are that f of x tends to 0 as z goes to infinity, f is smooth, okay, has the right proper decays and so on, so that this integral makes sense, okay? So this, we're integrating over the real line, but there's this z up here. Z equals to xc plus I zeta, okay? So this is not a singular integral because x does not see z, right? Z is up. So, and suppose that things are smooth, f decays, I put in those like 1 over x squared, whatever, things so that if you want to differentiate inside, you can, whatever, right? Let's not worry about that. Now, this is as a function of z, this is analytic. Okay? And now let's see that we're going to get the Hilbert transform, right? And let's see what the Hilbert transform does with real and imaginary parts in the upper half plane. Okay? So the first step is rationalize the integrand. So we can write this like this. Okay, I multiplied on top and on bottom by this, so I have a real valued denominator, so that makes my life easy. So I can write this. I'm going to skip one step because it's easy. Let's see if I copied correctly. Wait a minute. No, I didn't. This one I mixed up two things, sorry. I looked at the wrong. Let me double check because I just skipped one line to save us time. Yeah, I think I have it right. So what did I do? Okay, it's simple. So basically I rationalize, right? Then I write real and imaginary parts, and I just rescale it, rewrite it like this. Okay, so it's simple. So what? Because it's useful to write it like that, okay? So now for the first part, for the real part, note let's do so that we can recognize things. write this, define this as R, right? Note that Z, for the time being, right, for the moment. Later on I will not do this, but for the moment, Z is fixed. Then what I will do afterwards is to allow Z to come down, okay? But for the moment, Z is fixed, which means that Xi and zeta are fixed, so that therefore is equal to R, and this integral here is equal, let me put it like this, save us time. No, the integral is not exactly equal to that, sorry. Okay, so basically, and this, sorry, is equal to 1. So let me repeat it again because I'm talking and writing and trying to save time. So this first integral, now let me repeat the explanation so that I'm clear. From this first expression here, I look at this guy here, this variable here. I'm going to call it R, right? Z is fixed, so dx dr is this, right? Because it's fixed. Well, here is not xi. It's zeta, right? Yeah, the note is correct. It's zeta, okay? And this part here, forget about the f. Forget about the f. This part here, look, why am I doing this? Because we want to let zeta go to 0, right? So if I want to let zeta go to 0, I'm going to look at this guy, and whoa, when zeta goes to 0, something weird might happen. But no, it's not a problem, because let's forget about the f for the time being. If this guy, if I do this change of variables, this guy, right, without the f is this, which note that this is like a bell-shaped function like this, but with the amplitude growing. But if I do the change of variables and write it in terms of r, sorry, another mistake here. In the notes, I think it's correct. Yes, it is. It's my mistake on the blackboard. This guy here has total mass 1. So, and you see, this has to do with this guy is a bell-shaped function centered at xi, which has sort of a scaling with zeta going to 0. So this guy is going to become like a Dirac mass as zeta goes to 0, because it has total mass 1, right? It looks like a Dirac function, right? So as zeta goes to 0, what am I going to get from this? F evaluated at the center, as C. Just we can do with the Gaussian, we can do with the square impulse, right? I mean, we have to prove the continuity of it, but we did once for one kind of function for the delta function. Remember when we did distributions. So I'm not doing all the details, but you can say that as zeta goes to 0, which means as the z point comes closer to the real axis, this function here, which is a bell-shaped function, something like this, right? It's 1 over r squared. It will get skinny and tall with total mass 1. It's like a delta function, a Dirac delta function. So this is going to give me f of xi, because it's centered at xi. And as zeta goes to 0, what do I get from this one? This guy here goes to 0. And I'm just left with this. Okay, so I'm going to write this result. So in the limit, so now the result from this discussion is that in the limit of phi z as zeta goes to 0, this will be phi of xi, which is f of xi plus I. The Hilbert transform of f in xi. Right, where xi is going to be the same thing as x. Right? Do you agree? Minus, where's the minus sign you're checking for? Because this is going to be equal to, right? And right here. Then we check. Oh, because that minus sign, right? You're right. Because this is going to be, no, this is going to be the Hilbert. Just let me write, because you already checked it, but I'm not sure yet, so let's see. You help me. This is the Hilbert transform, right? Now you saw the minus sign. I'm lost with the minus sign still. Let's see. Why is the minus sign? It looked like it was wrong. Where? No, but why is playing the role of xi, right? Well, let me see. Oh no, of x. So here, x minus y. Ah, yeah. Yeah. This guy flipping, right? Thank you, Lucas. Thank you, Lucas. Right. So this guy flipping. Yeah. So here would be. So let me see. X minus y. Yeah. So here would be. This is the right way to write it, right? Thank you. Yeah, very good. Thank you. Okay. Thanks. That's good. So therefore, so you see, so as this guy came down, right? So since I made a mistake, let me repeat things. So thank you for helping me. So this is an analytic function, right? And this analytic function, I'm saying it's like this. This is the notation, right? The real part of this function, the imaginary part of this function, and this is the harmonic conjugate of this guy. Okay? So, when z came down, right, x and xi are the same thing, and y would be then, so as zeta comes to 0, this would be. This also happens when zeta equals to y equal to 0. Right? Just for notational reasons, we had the zeta in the thing. So this means, this is like f of x, right? Plus I, the Hilbert transform. So the Hilbert transform, see, is the trace of the harmonic conjugate. Okay, so it takes the Hilbert transform takes the trace. What means, why, right? Is it clear to you when I mentioned the trace? Because we're talking about a harmonic function on the upper half plane, and the boundary of the upper half plane is the real axis. Right? So this would be the trace, just the boundary value, the Dirichlet data. Right? This would be the Dirichlet data of this of f. Right? So this, look, this, right? This is the of this harmonic function. Of this harmonic function in the upper half plane. Okay? And the Hilbert transform takes that Dirichlet data, the trace, onto the trace of its harmonic conjugate. Okay? So that's a very nice property, right? So this is right, but this is the, well, I don't have to write. This is the harmonic conjugate of G. So this is one way of seeing the Hilbert transform. And the Hilbert transform, let me use this space here, right? It has to be shown, I will not show, but it has the property that it commutes with differentiation right? It's a singular integral, so we have to be a little careful in this sense that in this sense. Okay? Well, let me write down, let me put a U here. Oh, okay, I can leave the F. And I'll change the notation from the notes. Okay? But look, we have that f of x is equal to g of y, and f of y is equal to minus g of x. Correct? Cauchy-Riemann equations. They're harmonic conjugates. Okay? So this property here is very nice for two reasons. Number one, you can switch these guys, right? You can commute these guys having this very complicated singular integral operator, blah, 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 right? But one can prove that you can sort of exchange these two guys. And once I do that, I can see that for the half plane, right, the Hilbert transform functions as a Dirichlet to Neumann map. So I have to explain, I have some time, I'll basically finish with that. What is a Dirichlet to Neumann map? Well, a Dirichlet to Neumann map is this. So if I have a Dirichlet data here, right, I mean, suppose I have a, right, and this is the Dirichlet data here, right? The question is, can I have an operator that without solving Laplace's equation above, I give to this operator the Dirichlet data, and it gives me back the Neumann data. Remember that we saw using Green's third identity that the two guys have a functional relation, right? And that's nice, right? In some problems in numerics, I use this a lot, which is I don't have to solve the problem inside. I use the Dirichlet to Neumann map, and basically I have one and I get the other one. So for the Hilbert transform on the half plane, it gives me that. Why? Because look, if this is G, do you agree? The Hilbert transform of F is G. We just saw that. But Gx, so this is Gx. Oh, but Gx is minus Fy. Okay? Which is here minus Fy is df dn, which is the Neumann data. So if I take the Hilbert transform of the, but I don't know what G is, right? But if I take the Hilbert transform of the derivative, the tangential derivative of f, which I can do it here, so if I differentiate my Dirichlet data here and do the Hilbert transform, I have the Neumann derivative there, which in fluids is very useful. In actually situations of this type, there's a famous equation, which is the Benjamin-Ono equation for waves. Which is like this. It looks like a KdV. It has a non-local term. So this is a Benjamin-Ono equation. Until recent people study many aspects of it and in systems and so on. And this problem, the Benjamin-Ono equation, appears in problems like this of internal waves. And this is a problem for a model for what's called internal waves. So what is internal waves? So in the ocean, right, this is sometimes the surface of the ocean. Okay, so let me put a little boat here so we know it's the surface of the ocean, right? And sometimes the ocean is stratified, right? Which means it has fluid 1, fluid 2 in the ocean. What does that mean? It means, for example, for temperature reasons, right? The sun heats up this part of this layer, it becomes lighter, and this blue part is much colder. Suddenly it becomes much colder. And that then supports this interface. We saw an interface for that problem. That supports what's called an internal waves. And internal waves sometimes can be huge. For example, in the Strait of Messina, which is near the tip of the boot of Italy, they have already observed internal waves, which usually are waves of depression. So sometimes like this. Okay? And actually you can actually deduce KdVs for it and so on, or Benjamin-Ono equations for it. This amplitude of this wave here, almost 100 meters. It's a huge wave. But that you barely see it from the top. Sometimes in the top you see just where the wave is, you see a little ripple from satellites. Right? So if you put in Google internal waves and the Strait of Messina, I think it writes like this, Messina. In Italy, there's some beautiful photographs of the surface and explanations and so on. And the Benjamin-Ono equation was a reduced model, as we learned, right, for this type of waves, where you imagine that you have potential theory here, potential theory there. The top layer is not very deep, and the bottom layer is infinite, right? And then you have to find the normal derivatives, whatever. The Hilbert transform comes in a little bit in the flavor as a Dirichlet to Neumann map operator, right? And you see this equation now is an integral differential equation with a singular integral, and when it's coupled to other equations and so on. So, for example, Felipe Linares here at IMPET and other people, Jerry Bourne and many names, study the well-posedness, if there exists, also traveling wave solutions in this test for the Benjamin-Ono equation, and the Hilbert transform appears in this nice way. I want to give you one more example of a Dirichlet to Neumann map. It's kind of simple. All right, let's see. But I don't want to rush. Yeah, I'm going to leave this for the beginning of next class. And I think I want to give you back I think I'm going to stop here because I want to give you back the homework. Parar aqui, então. Obrigado. And we can talk a little more in private.